Good morning, good afternoon, good evening. This is Michael Herman, and this tutorial is on the Web 7.0 Trust Spanning Layer Framework, and specifically how to perform SAM-stack analysis. And the specific example we're going to use here is the DIDComm over HTTP model for Web 7.0. And so we're going to go through the analysis steps, step by step, and build out the DIDComm over HTTP spanning layer SAM stacks. SAM stacks owes its name to Sam Smith, who recently gave a presentation to the Trust over IP Foundation regarding the idea of spanning layer stacks, and so I'm referring to those now as SAM stacks. So each step of the process is going to be documented by a slide like this, which I refer to as the Web 7.0 SAM stacks analysis process. And so we start out with the goal, which is to decompose a DIDComm-ARM, a DIDComm architecture reference model, into one or several SAM stacks, and we'll see what those are in a moment. The additional steps to realize that goal are SAM stack analysis or partial decomposition, SAM stack synthesis, where we create a SAM stack for each unique relationship in the DIDComm-ARM model. And then we create a visualization, and for lack of a better name, I've called it a SAM stack slam. And if you can say those three steps quickly without making a mistake, you're a good person. So the target here is the Web 7.0 DIDComm architecture reference model. More specifically, this is layer 6 of that model. And within this picture, and I'm going to highlight them individually in a moment, we have 4 or 5 different DIDComm agents, and they all have relationships to one another, and you would expect that they use the DIDComm protocol to talk to each other. And we have what I call some internet services. So those are services, basically anything that doesn't use DIDComm, and so the DID registry is an internet service, and in the more detailed model, we'll actually front end that with a DIDComm gateway. So we'll have the DIDComm DID registry gateway, so that we will end up speaking DIDComm to everything in the Web 7.0 architecture. And you can imagine what that'll do for the trust spanning layer and for the trust spanning layer SAM stacks. So let's look at this model in a little more detail. So the purple box is a traditional regular DIDComm agent. Beside it, we have a DIDComm client. A DIDComm client is different from a DIDComm agent in that it only has an outbound origin interface. And we can see where the green arrow and the purple arrow come together. That's out of the bottom of the DIDComm client. That's the origin interface. If we go back to the DIDComm agent, it has both an origin interface and a service endpoint. At the top, we have a DIDComm user agent. A DIDComm user agent is a special type of DIDComm agent that projects a user interface, a user experience. Think of that as a DIDComm agent that runs on your phone. And that DIDComm agent is paired with a regular DIDComm agent. The DIDComm user agent is paired with a regular DIDComm agent, and so the yellow agent at the top is paired with the purple agent underneath it. And that purple agent may live on your laptop, on a tablet, perhaps on a DIDComm appliance running at home, in your office, or in a data center. On the right is the DID registry. The DID registry is different from the previous elements in that it's an internet service. It's speaking more traditional TCP/IP and internet protocols. and it is specifically not using DIDComm. As I mentioned a moment ago, when we get into the details of the network architecture, this DID registry is actually front-ended with a DIDComm DID registry agent gateway. At the bottom, we have the DIDComm network. The DIDComm network is a network of DIDComm network router agents, special purpose, specialized DIDComm agents that solely undertake the task of network routing. Now we have two elements that are left uncolored, the DIDComm notation element on the far left and the DIDComm notation second from the right. These ones that are highlighted in red. These are not active network or Web 7.0 components. These are what we call personifications. The barn on the left, the farm business, is a personification of the DIDComm agent in the purple, and the red ABC grocery personification is a personification of the DIDComm client in the blue box. If you want to learn more about personification, you should read the Web 7.0 DIDComm-ARM white paper. You can find that at the top of the hyperonomy.com blog. That's hyperonomy, just like it sounds. So let's take this as our starting point. This is the DIDComm architecture reference model that we want to decompose. Previously, I had created a trust spanning layer framework model. At the top there, I've labeled it the all-in or the kitchen sink stack. This was a version 0. This was a first cut. The most important thing it did is it helped inform or educate users of the trust spanning layer framework that there's many things that are part of the DIDComm ecosystem. DIDComm is not a word to be used by itself, just like we shouldn't be using SSI by itself and other terms in the decentralized vocabulary. DIDComm has various elements, DIDComm messaging, which in turn is comprised of DIDComm messages that can have DIDComm attachments, and that all works together as a process, if you will, as part of the bare credential sender receiver model. So that's what I've just highlighted in the blue area. And we're not going to go through all of these. Not all of these are network elements. Some of them are just part of the DIDComm-ARM architecture. What we're really trying to do is take that kitchen sink model and break it down into a bunch of SAM stacks focused on different aspects of the architecture. So let's look at how we do that. This is the following step is when we'll actively do the SAM stack analysis or partial decomposition of the DIDComm-ARM. So the first thing we did is use the DIDComm notation, use those elements that we're familiar with from the DIDComm architecture reference model. And I've just redrawn, actually on a piece of paper originally, I redrew that previous DIDComm-ARM layer 6 model. And so we can see in black that there's 5 DIDComm agents or specializations of DIDComm agents. Close to the number 7, there's the standard or regular DIDComm agent. To the left, on the end of the line, arrow number 6, is the DIDComm user agent. To the right of this number 7 DIDComm agent, at the end of the arrow number 8, is the DIDComm client. In the bottom left, we see the DIDComm network message router agent. And to the far right, the agent that we see there is the DIDComm registry gateway. It's a specialized DIDComm agent that gives us DIDComm access to the DID registry. We see a pair of DID registries in the far right bottom corner of this diagram. And the reason for that is that DIDComm DID registries can be chained together and front-ended by one or more DID registry gateways. In the bottom center, we see a pair of DNS servers. Again, DNS servers are similarly often deployed in pairs, either pairs, but usually physically separated in the network. And then we see all kinds of lines, network connections. The green connections represent DNS protocol connections. The bright blue lines represent DID registry protocol connections. The purple lines represent conventional DIDComm communication paths, and the similarly shaped or shaded blue lines, numbered 10, those are specialized DIDComm protocol connections to support message forwarding. You can see that they move in and out of the agent nearest the number 12. That's the DIDComm network message router agent. So this is our partial decomposition. We've enumerated all the possible network connections and we've numbered them. And the way that we're going to proceed with the SAM stack analysis is by building a SAM stack for each numbered relationship, for each numbered connection between each pair of elements in Web 7.0. And then we'll bring those together. That's what we call the SAM stack SLAM. And we'll put them into two stratas, into two layers. And from that, we'll be able to deduce the trust spanning layers for Web 7.0. To help automate some of this process, we encoded that previous diagram, and I'll show you the encoding on the next slide, and ran it into Neo4j to do a visualization. Neo4j is a popular graph database, and they have a very popular free desktop version of it. And so the red dots at the bottom, the red vertices at the bottom, those correspond to what I call, the internet services, the ones that don't speak DIDComm. And so on the left, we have the pair of DID registries, DR1 and DR2. And on the right, we have the pair of DNS servers, DNS1 and DNS2. Across the top, we have DUA1, which is the DIDComm user agent. In the middle at the top, we have DA1, which is the conventional DIDComm agent. And on the far right, we have the DIDComm client one. Coming down the left side in the middle, there's the DIDComm routing agent, message routing agent. And the one DIDComm agent that's left, the bottom lowest one in the diagram there, that's actually the DIDComm network routing agent, the one in the bottom. The one on the left, I stand corrected, is the DIDComm DID registry gateway. So just to clarify my correction, down the left side in the middle is the DIDComm DID registry gateway, and in the bottom is the DIDComm network message routing agent. And this is a piece of Cypher, Neo4j Cypher language, in which we've encoded the previous diagram, or the original diagram, and it's from this ciphertext that we were able to automatically generate the previous diagram. If Daniel Hardman is watching, this might be the language we've been looking for modeling decentralized systems. Not to go into a lot of detail, but if you look right down the center of the slide, you'll see that, for example, where the protocols are specified, it's an array of protocols. So we can actually specify an entire protocol stack as metadata for each of those lines, for each of those connections between the DIDComm agents and between the and between the DIDComm agents and the internet services. The 5 DIDComm agents and the specializations of the agents are defined at the top: agent, user agent, client, network message router, and DID registry gateway. Below that are 4 internet services: the 2 DNS services and the 2 DID registry servers. Okay, so with that partial decomposition, let's start with the SAM stack analysis. And what we're going to create is one SAM stack for each unique relationship, each connection between a pair of elements in the DIDComm-ARM. So here's the first one. This is a DNS client service stack. So we have the 4 DIDComm agents that might need access to the to DNS. Probably should be all 5 of them in here. And we can see that it's using DNS over TCP or UDP to access the inbound connection, the port 53 connection on the DNS server at the very bottom. Each one of these SAM stacks will be simple, like this, highlighting just a few features. And we'll go through quite a number of these, and then we will do the SAM stack SLAM to organize these into layers. So here, DNS forwarding. It's important when you're doing SAM stack analysis to make sure that you capture all of the network connections and not just the obvious ones. So for example, the fact that we have a pair of DNS servers means that we have to highlight that DNS1 is connected to DNS2, and that's a DNS forwarding operation. And so that green line is running standard DNS protocols. We've also carried the numbering through. It's important that we capture all the connections that we found during the decomposition, and all of these SAM stacks start to look the same after a while, so we attach the network connection numbers to the SAM stacks. This SAM stack is the DID registry gateway, DID registry service stack. So at the top there, we have a DIDComm agent, the DIDComm registry gateway agent, and it's allowing us to use the DIDComm protocol to query the DID registry. And we can see the DID registry there at the bottom. It passes DIDs over TCP/IP/UDP. So we classify this as an IPv4 protocol when we get to the SAM stack SLAM, but we're actually passing DIDs specifically over TCP or UDP between the DIDComm registry and the DIDComm registry gateway and the DIDComm registry. The DIDComm registries, the DID registries, also can perform forwarding similar to DNS. So again, just being anal and being complete, we have the DID registry to DID registry forwarding stack, and that's number 4. You can refer to it back to the earlier slide, and of course it's running DNS over TCP/IP/UDP. SLAM stack number 5 is showing the pair of DID registries, or a DID registry being connected to a DNS server. This is going to seem very mysterious, and I'm not going to go into any explanation here, but just trust me that it works. So we end up with a chain of DID registry 1 forwarding to DID registry 2, DID registry 2 forwarding to DNS1, and DNS1 forwarding to DNS2. We're now on more common ground. This is the DIDComm over HTTP user agent stack. So at the very top, we can see the DIDComm user agent, and at the very bottom, we can see the DIDComm agent that it's paired with. This may seem a little odd from a trust spanning layer framework perspective, but in this case, the DIDComm agent at the bottom is actually acting as a foundational layer, providing storage and communication services to the DIDComm user agent. Again, the DIDComm user agent is a specialization of a DIDComm agent, and then it provides a user interface or user experience. It's a way for a human to interact with the DIDComm network. And it's numbered 6. Here we have the DIDComm agent-to-agent stack. So of course, DIDComm agents can talk to DIDComm agents, and that's all we're highlighting here. We have the outbound origin interface talking to the inbound service endpoint on the bottom, and from the bottom we have the outbound origin interface of that bottom DIDComm agent talking to the inbound service endpoint on the top agent. And that's numbered SLAM stack number 7. Of course, all of these are running, quote DIDComm, but we don't like to use that word by itself. More specifically, they're using the bare credential sender-receiver model. And this is a foundational protocol. This is part of the trust spanning layer for Web 7.0. It is only reliant on DIDComm messaging, DIDComm messages, and DIDComm attachments. On the top right of the original diagram, there was a DIDComm client. A client is different from an agent in that a client only has an outbound origin interface. We can see that at the top. And so that outbound origin interface usually talks to a traditional DIDComm agent at the bottom to the inbound service endpoint. Again, this is primarily there for completeness. This is the DID registry gateway DIDComm client service stack. So what the heck do we have going on here? So at the bottom we have the DID registry gateway. This is the DIDComm agent that sits in front of the DID registry. And I've only highlighted one of the connections, the one from the traditional DIDComm agent, from the origin outbound interface to the inbound interface on the DID registry gateway. So when a DIDComm agent, whether it's a user agent, a DID client, or one of the network message routing agents, when they need to resolve a DID, they will send that as a DIDComm message to the DIDComm registry gateway, and the DIDComm registry gateway in turn will query the DID registry. This is all described in the DIDComm-ARM white paper, and the main purpose of this presentation is not necessarily go into all of those details, but I want to give you enough detail that if you haven't read the white paper, it makes a tiny bit of sense. This is SLAM stack number 9. SLAM stack number 10, SAM stack number 10. This is an agent talking to a DIDComm network router agent. So at the bottom with the little traffic light there, that's the DIDComm network message router agent. That's how we define it in using DIDComm notation. And we can, again, we've just highlighted the connections to a traditional DIDComm agent, but it could be a user agent or a DIDComm client, all talking to or forwarding messages through the DIDComm network message router agent. And again, this is using bare credential sender-receiver model. More specifically, it's using the DIDComm message forwarding protocol. And so once messages are forwarded to that DIDComm network message routing agent at the bottom, then the messages are in the network. And it is a network of one or more network message routing agents that perform that intelligent message level routing capability. It's also these network message router agents that support disconnected agents, that is, agents that are either not running at all or agents that are not accessible because they're behind a firewall. In that case, the network message router agent also acts as a cache for these auth encrypted messages, and they will stay in the cache until that agent, disconnected agent, comes online. This is the network router to network router agent stack. So this is the stack. This is the blue dots in the original layer 6 model. So once an agent drops a message, let's say into that top network message router agent, that agent talks to other network message router agents to intelligently deliver those messages through the network. The description of how the message routing occurs is in the part 2 model, or the part 2 tutorial that describes the DIDComm-ARM model. And it is also described in the DIDComm-ARM white paper. This is SAMstack 12. This is SAMstack 13 and the last one. So these higher numbered ones were ones that were maybe forgotten initially and added in. This is the DIDComm registry gateway to DIDComm registry gateway agent stack. And so this is where you have a DIDComm registry gateway who maybe is unable to resolve a DID, and so it may have a secondary DID registry gateway to forward that request to. Out the right side of each of those DID registry gateways, we can see that there's a DID over TCP/IP connection, and that is used to send the DIDs against an actual DID registry. But if the one at the top fails, then the purple path will be used to try the second one. These, of course, use the bare credential sender-receiver model. So that's it for the 13 DIDComm-ARM SAMstacks. So we get to the colorful step 3, which is the SAMstack SLAM. What we're going to do is essentially take smaller versions of each of those SAMstacks and start organizing them into layers and placing them conceptually onto a large canvas so we can see and understand what are the actual trust spanning layer protocols. So we run into a problem right away with SLAMstack 10, because what we've actually mixed on that slide, on that SLAMstack number 1, is we have the agents, which typically are speaking DIDComm, but they do have to talk to a DNS server, so they're using DNS over TCP/IP. So there's something we call SAMstack stretching, which is a technique you need to use sometimes during this stage of the synthesis process. So what we're going to do is essentially take that SAMstack and split it into 2. And we're going to introduce the purple line. The purple dashed line is our separator between those SAMstacks that use DIDComm messaging and those SAMstacks that use IPv4, IPv5 internet protocols, i.e. primarily DNS for the DIDComm-ARM. So at the bottom now, we've got the bottom half of stack number 1, which is the DNS server. And it accepts, DNS over TCP, UDP, port 53. And then the top half of stack 1, we've separated that and put it above the line. Not that there's any DIDComm messaging happening in this stack, but it'll help with alignment issues later on. So we refer to this technique of splitting a single SAMstack into 2 SAMstacks as SAMstack stretching. And we will to look at the others. So we have to include DNS forwarding in here somewhere. So let's take the SAMstack number 2 and we'll just put it alongside SAMstack number 1. SAMstack number 1 is the DNS server. Makes sense to put the DNS forwarder right beside it. And so the intention here is to illustrate how DNS forwarding works. that it uses DNS over TCP/IP/UDP, and of course there's a natural connection between SAM-stack number 1 and SAM-stack number 2. Let's start with SAM-stack number 3, which is the registry gateway talking to a DID registry service. So remember, the DID registry gateway is a DIDComm agent that accepts DIDComm messages on its inbound service endpoint, and it speaks DIDs over TCP/IP to talk to the DID registry service. So the DID registry service is not a native DIDComm agent. We want everything to be DIDComm in Web 7.0. So this is illustrating that DIDComm agent sitting in front of a traditional internet service. In this case, it's the DID registry service, or any service that just doesn't speak DIDComm. It's a pattern. And of course, on top of that, we can add SAM-stack number 9. SAM-stack number 9 shows how all the different kinds of DIDComm agents, DIDComm agent itself, the DIDComm user agent, the DIDComm client, and the DIDComm network agent, how they talk to the DIDComm DID registry gateway. That's what we see at the bottom of number 9, and that DIDComm DID registry gateway then appears at the top of SAM-stack number 3, and that's how any of our DIDComm agents at the very top cross the purple line and are able to access DID documents in the DID registry at the bottom. Again, it may seem a little obtuse. I refer you to the Web 7.0 DIDComm-ARM white paper. DID registries have the ability to forward requests. If it's not able to satisfy a request, it can forward it on to another DID registry server. That's a TCP/IP operation, and we see that represented here. We're able to slip in a fourth SAM-stack into the SLAM here. Number 13 is how DIDComm registry gateways can talk to themselves, exchange messages with each other. That's using DIDComm, that's using the bare credential sender receiver model, so it lives above the line and is a natural complement to the other 3 SAM-stacks here. We start to see the pattern emerging where there seems to be a lot of SLAM stacks across the top above the purple line that are using the bare credential sender receiver model. And then we have a number of internet service-based SLAM stacks, primarily DNS and DID registry-based components that are using primarily TCP/IP as their native protocol. Oh, we have one orphan here. This is the DID registry to DID registry forwarding stack. So this is really a complement to the previous 4, but there wasn't room on that slide. And this is showing how if one DID registry is not able to satisfy the DID document for a particular DID, it can forward it. It can be configured to forward it to a second DID registry server. In addition, and this is where I did a little bit of hand waving before, SLAM-stack 5 is showing how a DID registry server can also forward requests to a DNS server. So in fact, what we've implemented here is the ability for a DID registry server to satisfy not only DID documents based on DID queries, but a DID registry server can also satisfy DNS requests by forwarding them to a DNS server. By the implication here is that our DIDComm DID registry gateway, that gateway that speaks DIDComm, can also field DNS requests in addition to DID document requests. This is the DIDComm over HTTP user agent stack SLAM number 5, SAM stack number 5, and again, it's just the user agent talking to a regular DIDComm agent. It lives entirely above the purple line. And then we can also have agents talking to agents in SAM stack number 7, and we see that illustrated here. Eventually, we're going to end up with all the SAM stacks either above the line or below the line. Here we have the client agent talking to a DIDComm agent. That's kind of the analog of the previous one. This is SAM stack number 8. Here we have the last two SLAMs. This is SAM stack 10 and SAM stack 12. SAM stack 10 is how a DIDComm agent and its specializations can talk to a DIDComm network router agent, message router agent. So we see the 3 conventional kinds of DIDComm agents at the top, and below the number 10 there we see the traffic light that signals that this is a DIDComm message routing agent. And as you'd expect, the sort of the orphan at the end of the SLAM here is the forwarding agent that allows network routing agents to talk to network routing agents. So now we've seen on the previous slides the 14 individual SLAMs. Here they are aggregated onto one slide and almost illegible. But you can see in the top, they're all based on the bare credential sender-receiver model, i.e. DIDComm messaging, DIDComm messages, and DIDComm attachments. And in the bottom, although there's sort of 2 kinds of protocols, we have DIDs running over TCP/IP and DNS running over TCP/IP. This is the TCP/IP layer. These are the what I call the internet services, the ones that are running over TCP/IP or UDP. And so these are functionally below, they're foundational, if you will. But if you take each of the layers separate and distinct, we have TCP/IP as a spanning layer protocol on the bottom, and we've got the bare credential sender-receiver DIDComm model as the trusted spanning layer and trusted spanning layer protocol in the top half.
This is an addition to this Web 7.0 trust spanning layer framework, specifically an addition of a 4th step to the SAM stacks analysis process. Daniel Hardman observed that in the previous SAM stack, in this SAM stack SLAM, Daniel Hardman noticed that, in the bottom, he wasn't content with all the different DNS servers and DID servers spanning the level 2 trust spanning layer, and I tend to agree with them in hindsight. The process that got us here, the first 3 steps, were really quite mechanical. In fact, the creation of these, the SLAM stack, could in fact be almost fully automated based on the steps that we discussed. So I've decided to add a 4th step, which I call SAM stack restacking. It's an optimization phase where you take the process of the results of the automated SLAM stack analysis process, and you look carefully, particularly when you end up with 2 strata like this. And if we look at the bottom strata, where really the issue is, you could contend that unlike the DIDComm protocol, which is by nature a trust spanning protocol, maybe DNS isn't of that same ilk, that same kind of animal. So to apply step 4, the SAM stack restacking, we're going to take the SLAM stacks highlighted in green and do this to them. We're going to create a DIDComm agent, DIDComm did registry gateway restack. And this is going to more faithfully meet the conditions or the intent of the level 2 trust spanning layer. We can see the different kinds of agents above layer 2. They're using the bare credential sender receiver model to access the DID registry gateway DIDComm service. They're using DIDComm connection number 9 to do that. And then if we look at the agent in the bottom center there, the DID registry gateway, the DIDComm DID registry gateway, it's in the foundation layer where it belongs. And then to the right of that is the chain of 2 DID registry servers and the 2 DNS servers. And they use DNS forwarding to pass unresolvable requests. So if the DID registry gateway receives a DID request over DIDComm, it will use connection number 3 to pass that to the DID registry number 1. If that DID registry is unable to resolve it, it's going to pass it to over connection number 4 to DID registry number 2. And if it isn't able to resolve it, for example, maybe it's not a DID, maybe it's actually a DNS domain name that needs to be resolved, that'll be passed over connection 5 to perhaps a local DNS server, DNS number 1. And if it's not resolvable, then it might be forwarded to a DNS server out on the internet. And so on. So that's connections number 2 and number 11. So when we do this restack, when we combine most of those SAM stacks that were below the purple line, we end up with the following. The SLAM stack that we were just looking at, it replaces SLAM stack number 1 above the purple line, the green box. And below it, the purple line, we only end up with one SLAM stack. This is traditional DNS. So any of the any of the 5 DIDComm agents, specializations of a DIDComm agent, they need to access DNS. They need to be able to look up service endpoint URLs and those sorts of things. So we just have a very simple SLAM stack number 1 still resides below the line, accessing DNS in the traditional way. And just to emphasize that a bit, let's look at that last SLAM stack SLAM, the one of the result of the step 4 restacking. And if we just kind of zoom in on that on the green one there, the restack, just to remind us, what it looks like. Any of the 4 DIDComm agents or their specializations can use a number 9 connection to contact the service endpoint of the DIDComm registry agent at the bottom. And the purpose of the DIDComm registry agent is very, very simple. It's to take an incoming DID, possibly specified in the DIDlang language, and it acts as a gateway, a transformation point for taking DIDs over DIDComm and changing those into DID requests over DNS port 53. And DNS port 53 is used for all the subsequent communication paths outlined in green. Thank you, Daniel, for indirectly suggesting the improvement.
So that was a quick fire hosing. I hope it illustrates or gives you a sense for the SLAM stack analysis process. There's the 3 steps. We do the partial decomposition. We build the individual SLAM stacks. And then we do the SLAM. We group the SLAM stacks above a particular interface line. Now for Web 7.0 and the DIDComm-ARM, it was by design intended to be almost exclusively based on the DIDComm messaging protocol, DID communications protocol. And so it, being well designed from the beginning, ends up with a well-designed set of SAM stacks and a well-designed, SLAM at the end. So I thank you for watching and look forward to getting your comments and feedback on the Web 7.0 SLAM stack analysis process.